Dr. Borsha Nyong with us. So on behalf of organizing committee and my own behalf, I welcome you, madam.
Thank you. Thank you, sir.
So Dr. Borsha Nyong obtained her BSc from Jagannath
Borua
College, Jorhat, Assam. She completed her MSc and MPhil in statistics from Dibrugarh University. It's a very renowned university in the Northeast.
Yeah.
So presently, she is working as assistant professor in the Department of Agricultural Statistics, Assam Agriculture University, Jorhat. She has published more than 12 research papers in national and international journals. She has organized national level workshop in collaboration with national institutes. She has supervised several MSc and PhD students as a supporting guide. She has participated many national international workshop and conferences, as well as presented her research work in national international conferences. She has been invited as a resource person in national level workshop and conferences. Her research area includes forecasting, machine learning, and time series analysis. So it was a brief about our today's resource person. So with this, we welcome you, ma'am, and thanks for joining this platform and for being with us and giving your valuable time to our participants. So on behalf of participants, I welcome to you, madam. So ma'am, we'll take the session on this inferential statistics. So over to you, ma'am. Thank you.
Yes. Good afternoon to all of you. Then actually that first of all, I just want to say thank you. Thank you just want to say thank you Science Tech Institute for inviting me as a resource person. And that today's session actually I'll cover on statistical inference on health sciences. So now I am sharing my screen. So I am Borsha Nyong. You have already known that I am Borsha Nyong from Assam Agriculture University. So here my presentation. I am sharing my presentation. Okay, so is it visible now, sir?
Yes.
Yeah, okay. Okay, so that actually the topic that today I'll cover on inferential statistics in health science, but it is a vast topic. So, but that in statistics actually we divide it into two types. So two parts. Then one is descriptive statistics. Most of you may know about descriptive statistics and inferential statistics. So that's why that descriptive statistics gives only the describe about the data. So that descriptive statistics gives about the concentration of data. That means under measures of central tendency, measures of dispersion, those are under the descriptive statistics. But actually under inferential statistics, what we do, so we do that that we collect some sample from the population. We draw the interpretation about the using those sample values. We interpret the data based on the population. So that is the inferential statistics. So we have actually lots of statistical methods under the inferential statistics. So here what is actually that that is the definitions of statistical inference. So that using the sample, so how can you draw the interpretation about the population? Because due to some actually lack of factors, we can't able to collect all those data, all population data. So that's why we have to select some proper sample. Okay, so using those sample, we just using those sample, we just give the interpretation about the population. So that's under the statistical inference. So usually under statistical inference, actually this is under statistical inference, there are two kinds. One is parameter estimation and one is the hypothesis testing. So what is actually parameter estimation? So the parameter estimation is concerned with the only the numerical value of the parameter. So what is parameter actually? First we have to know that is what is parameter. So parameter actually is what? It is actually related with the population. And statistics, there are two terms, the parameter and the statistics. Okay, the parameter is related with the population and statistics statistic is related to the sample. But what is actually that parameter means that's the constant value. So that is, suppose for example, the population mean. So the measures of central tendency, population mean, population standard deviation, population variance. So those are the parameter because these are related with the population. Using the population value, so we can estimate the parameters: mean value, median value, standard deviation, and variance. And the what is statistics? So statistics actually it is related to the sample. This is coming from the sample, and the means what, that sample is actually what the sample mean, sample standard deviation, sample variance. So that is the statistics. So here the term is, under the statistical inference we have two kinds. One is parameter estimation and one is hypothesis testing. So now today we'll deal with on the only on hypothesis testing. So what is actually hypothesis testing? So this is just an assumption. So based on some assumption, so we can draw the interpretation about the population parameter. Okay, so that means this is the main concept of statistical inference. So under actually, so here under the hypothesis test we have actually two types of test. One is parametric test and one is non-parametric test. So under the parametric test, so there are different actually types of test. So based on some actually what sample size, based on some numbers of samples, so we have divided actually the different types of test. Okay, so that under the parametric test we can apply t-test, we can apply z-test, we can apply t-test for difference of mean, paired t-test. So these are the techniques, these are the tests under the parametric, and then under the non-parametric we have different types of tests. These the list are the given here. So list of non-parametric tests are given here. So but actually what under this actually test that we have some difference between parametric test and non-parametric test. The conceptual question is what is the difference between parametric test and what is the difference between non-parametric test, and when we apply, we can apply the parametric test, when we can apply the non-parametric test. So that is the most important actually question. So because what is the parametric test? Usually the parametric test follows the normal distribution. If that actually this is the simple definition of the parametric test and non-parametric test. If you can check this slide, so you can actually able to understand the difference between the parametric and non-parametric test. So what is parametric test? So parametric test is one to which have some complete information about the population parameter, and that can make assumption about the parameters of the population distribution from which the samples are drawn. So that means what actually this line actually gives the concept. So because what we do in statistical inference, we take some samples from the population, from the particular population. So then we will make some assumption, under basis of that assumption we'll take the test statistics. So based on the test statistics, so then we actually we calculate the value of the test statistics, then we compare that value of the test statistics with some the critical value. So this is actually just that what the general actually steps for actually what the formulating for finding the value of for finding the value of the any statistical test, any parametric statistical test. Okay, so this is the definition of the parametric test. And the under non-parametric test, so it is what, if you have no any information about the population parameter, so we actually we cannot actually take the specific assumption. So on that cases, we can use the non-parametric test. And the most important one is what? If data set follows the normal distribution, so then we can use the parametric test. If data set means what? The sample values, whatever you have actually, what the selected samples is, it may vary from what the different researcher to researcher. Okay, so usually what we do in statistics, what we do, we use some samples and we collect those we use some samples and we used different statistical methods, so then we interpret the data set. Okay, so that first actually that sample values should follows the normal distribution, so then we can take the parametric test, we can use the parametric test. If the data set does not follows the normal distribution, does not have any pattern, so then we can use the non-parametric test. So under the measurement level, this is one of the most actually what the important difference between the parametric test and non-parametric test. So that's why for any data set, we must we must check the what actually normality test of the sample values. So under measurement scale level, so we have actually in statistics, we have 4 measurement scale. So we'll discuss it later. So that under the scale of measurement, we have ordinal scale, we have nominal scale, we have interval scale, and we have ratio scale. And in parametric test, so that for data set that should follows interval or ratio scale. And under non-parametric test, it follows the nominal or ordinal scale. So in measures of central tendency, so measures of central tendency under parametric test, it follows, it use mean, and under non-parametric test, it use median. And what is the applicability? Applicability means what are the under the parametric test, we can use only the quantitative variables, but under non-parametric test, we can use the quantitative variable as well as the qualitative variable. So what is qualitative variable? That is attribute. We cannot actually quantify it. Okay, so this is the difference between the parametric test and the non-parametric test. And under the parametric test, actually under the second point, so here I have written this actually what the basis of the normal distribution. If data set follows normal distribution, then we can use parametric. And if data set not actually does not follows any normal distribution, and no assumption can be made about the population distribution, then we can use the non-parametric test. So here the nominal, the scales, the different types of scales. So we have 4 scales. So nominal scales, ordinal scales, interval scales, and ratio scale. So what is actually nominal scale? So under the nominal scale, actually we have only 2 categories, like as binary. Binary means if have 2 categories, for example, gender. For example, suppose you are going to collect some information using questionnaire. So if you have some statements may have, suppose yes, no, like that. So that is that we can use the nominal scale. So there have no any characteristics. See that means variable does not follows any the character. Okay, so like that, that is actually the under the nominal scale. And what is actually ordinal scale? So it follows some order. So it follows some rank. Okay, so rank. So that means low to high. Okay, so that means first rank, second rank, third rank. So it follows some order. Then we can actually apply on that types of variable. We can categorize into the non-ordinal variable. So what is interval variable? Interval measure. So interval measure is what actually? So it is a fixed unit of measurement. For example, yes, so here examples are given. So measures of temperature. But here actually that we can means what we can take the zero have some meaning. Zero actually usually what we do. So that means what the in zero have no meaning. So like interval, under the interval scale, sometimes this is actually we can means apply the zero have some, we can actually assume the zero have some meaning, and the ratio that actually what the scale has a fundamental 0 point, or that is A's income. Here actually under the actually interval and under the 4 actually scales, so ratio scale is the best scale. So why actually ratio scale is the best scale? So this actually follows all the characters of any variables. So what is then, if you can see some examples of any variables, so then you can actually what the means that clear means you can able to understand from these actually types of examples under different types of scales of measurement. So that means I have already mentioned, if you have any binary variable, so then we can actually use the nominal data, that is the nominal data. So then we can categorize that variable as a for nominal. Okay, so then if you have some order, for example in suppose hill sign, so there may have some scale. Okay, so 5 Likert scale, 3 Likert scale, like that. So maybe actually, so that in health science research include pain scale 1 2 3 4 5. So accordingly we have that we put some scores, highest score 5 is more pain, the lowest score 3, suppose 2, then it is actually follows some order. So it is belong to under what non-ordinal data. So interval scale, so as I have already that told that interval scale is what actually, so it have some zero have some meaning. So for example, if actually what the that 100 degrees Celsius is 2 times, actually if 100 degrees Celsius is 2 times hotter than 50 degrees Celsius, it is not like that actually what the zero means no temperature, right? So that's why that we can apply the data, we can apply these types of variable. If you have any constant actually unit of measurement, so then you can use the interval data. Interval, then we categorize that variable for interval, and for ratio we can apply any numbers of any actually what the types of variables which have some quantitative value. Okay, so that we have actually different types of test, so under parametric and non-parametric. So for actually different purposes we can apply the parametric test and non-parametric test. For example, if you have only one variable, okay, if you have any only one variable, for example weight, for example age, it may be actually depends on the researcher, then we have some actually what the statistical test. Okay, so based on some variable, based on some data set of the univariable, so we can use t-test for single variable, t-test for single mean. Then and accordingly, if you have two variables, if that variables, those variables are independent, then we can apply the independent sample t-test. And if that variables are dependent, so then we can apply the pair t-test. If that variables have more than two variables, so then we can apply the ANOVA. If you want to see the different means what the, we want to see the correlation between the relation between the variable between two variable, so then we can use the correlation coefficient. So usually what we do for checking the relation between two variable, usually in parametric we can use Karl Pearson correlation coefficient, in non-parametric Spearman rank correlation. Here this is the actually just here means what the different alternative non-parametric test with some parametric test. Okay, so for independent sample,
Yeah,
yes,
excuse me, ma'am.
yes,
Can you repeat the single variable we use t-test? This line, can you repeat it again?
Yeah, I can.
Please.
Okay, so actually in different statistical tests we have different application. Okay, so under t-test we have the application. So t-test for single mean, t-test for double mean, t-test for two mean. Actually under two mean again, we have two types of t-test. One is the independent sample t-test, one is the dependent sample t-test. But in statistics, what we say, pair t-test. Okay, so then t-test for correlation coefficient, in t-test for regression coefficient. In t-test for single mean, actually, if you have any variable, suppose age, then what we do, you have suppose some set of variables, okay, sorry, some set of data under age. Okay, suppose you have 10 numbers of observation. So then we have to assume some null hypothesis. Okay, for that, actually for that, under basis of that assumption, the null hypothesis is what, actually it is the assumption only. Okay, so under the basis of that null hypothesis, we can actually take the proper test statistics, because this is the single mean, and now actually the assumption that null hypothesis is always related with the parameter value. So that's why we have to assume the mean value of the population. Then we can assume the mean value, the population mean is this one or not. Okay, so this is our actually assumption. That assumption will be your null hypothesis. So I'll actually I have some actually what the examples for different tests actually, so then it will be more clear for you. So these are the different actually parametric tests and non-parametric tests. So here, so these are paired t-test, Wilcoxon rank sum test, unpaired t-test, Mann-Whitney test, Pearson correlation, Spearman correlation. So that means all the tests have some different actually non-parametric tests, because we don't know that actually dataset dataset follows actually the assumption or not. The assumption means what the parametric assumption or not. So that's why every parametric test have some non-parametric test. So that's why, but usually in health sciences, so that we deal with the non-parametric test, because that means what, basically we use some qualitative variable. So that's why mostly we use the non-parametric test. Okay, so but actually what we do, so first of all, the first step is to check the normality test. To check the normality test, because then we can follow the proper test. Then we can follow the the parametric test will be applicable, yeah, non-parametric test will be applicable. So that's why the normality test is very much important for that before actually we doing the analysis. Okay, so that that under non-parametric test actually, so we have actually, we can either graph basis of graphs, okay, on or some test also, we can actually the say that data follows the normal distribution or not. So why actually normal distribution? Because normal distribution is the most important distribution in or any sampling distribution, and any actually what discrete and continuous distribution. Maybe this is somehow actually what the means, not means what it is a mathematical one, but simply you just actually remember that these things, that data should follows normal distribution, because that every distribution, the t distribution, that chi-square distribution, that is sampling distribution, because this distribution is related with the samples. So that's why this is sampling distribution follows normal distribution if degrees of freedom is actually large. Okay, so now, so maybe some of you may ask about what is degrees of freedom. What is the actually minimum numbers of observation? Okay, so what is degrees of freedom? So in statistical test, in parametric test, okay, now I am discussing only parametric test. In parametric test, we have two types of test. One is the small sample based on the sample size. One is the small sample size test and one is the large sample size test. And in small sample size test, we use t-test and f-test. And in large sample size test, we use z-test and chi-square test. Okay, so that's why the same application we can apply for z-test. If you can see, check the state statistics for t-test.
Excuse me, ma'am.
Yes.
How
Yes.
could we decide that the small sample size tests
Yeah. I'm telling you.
less than 30 or something?
Yeah, yeah, yeah.
Okay, ma'am.
So no, this is actually the standard actually size. Some actually benchmark is there, so that that if the sample size is less than 30, so then we can apply the t-test and f-test, and if the sample size is greater than 30, so then we can apply the z-test or chi-square test. Okay, but somehow we can apply, because that's why the applications of t-test and applications of z-test are similar, but that is one, there is a one difference only. The population variance is unknown for t-test and population variance is known for z-test. Okay, so then actually on the basis of the sample size, we can divide it into two types of tests. That is not two types of, means based on the sample size only, small sample size and large sample size. So every actually what the this every test, t small t distribution t test, f distribution f test, chi-square distribution chi-square test, so they all the distribution related to every test, so this follows normal distribution. So that's why we have to check that data follows the normal distribution or not. Okay, so here, so this is using,
Ma'am,
yeah,
sorry to interrupt you, but
yeah,
why it is only 30? Means it could be 28, 25, 35,
no,
but
yeah,
it's
yeah,
30. Why?
yeah. So
What is
because
the
of
reason?
actually, yeah, so because of what
The question
actually,
hour can be done at the end. That will be much better because it is interrupting the flow of the explanation.
yeah, I will explain after actually what this
Yeah, we request to
this situation.
participants kindly ask your
Yeah, after my
queries after
presentation.
this presentation.
Yeah, if you have
That
any
will, I think,
queries, just
better.
actually, yeah, write it up. So then I'll
You
actually
can write in
discuss
the
with
chat
you.
box, so we will
Yeah.
take the answer, queries after the session.
Yeah. So okay, fine. So that means what now? Can I start now? Okay, now I'm continuing with
Yes,
this
yes.
actually probability curve. So here actually the normal distribution, the curve of the normal distribution is always bell-shaped curve. Okay, so that means what? It is a symmetrical curve. Based on this concept, actually we have divided into some region, critical value. So then level of significance, like that. Okay, so for actually any test, for doing any test, we have to take the confidence interval, we have to take the level of significance, and we have to see actually what the that actually we have to check the one tail test or two tail test. Okay, so this concept is coming from this normal probability curve. Okay, so that means what, the right tail here, this is the normal probability curve, and this under this curve, this is equal to 1. So we know that total probability is always equal to 1, and this curve is called a symmetrical curve actually. So in symmetrical curve, what we do in symmetrical distribution, this is the actually what the properties of symmetrical distribution, the mean equal to median equal to mode. Okay, so then means based on this, actually if data set follows on under, if data set actually the pattern of the data follows and means bell shape, so then we can say that data follows the normal distribution. So here actually I am given here. So then if you can see there are two graphs actually. The first graph is also a histogram, second graph is also a histogram, but if you can see the two graphs, so that first actually figure represents that data follows the normal distribution. The shapes of this curve, the shape of the graph is like as bell shaped, but under the second one, but it is not a bell shape, so that we can interpret the first actually data set follows normal distribution and second one is not. Okay, so now then this is the concept of the normal distribution using the histogram, and using the Kolmogorov's mean of, we can actually use, now we'll use the SPSS software. So I'll show you. So then how can you actually calculate, how can you find the value of Kolmogorov's mean of as well as the means what the statistical significance test value. Okay, so then we can apply, we can use the Kolmogorov's mean of test is for normality test. So here I have given So that means some steps for doing for checking the normality test in SPSS. So later we'll do it. So then under the test of significance, show here what actually that after normality test, suppose data follows normal distribution. So then we can apply any parametric test. So what is the first step? Fine. First step is the what? First we have to assume the null hypothesis as well as the alternative hypothesis. So what is null hypothesis? So usually null hypothesis is just the assumption of no difference. Okay. So simply this is the null hypothesis, and that we denoted by, this is a mathematical one, H naught. And sometimes researcher may use one-tail test and two-tail test. This is based on the alternative hypothesis. Okay. So why actually alternative? How can you actually what the check that my null hypothesis and alternative hypothesis follows the one-tail or two-tail test? Usually we use two-tail test. Okay. For example, suppose your null population has a specified mean mu naught. Now we have no any data set. Just this is a value mu naught. Okay. It mu naught, it is a only just numeric value. If the population mean is mu naught, so your null hypothesis is for mu equal to mu naught. That means population mean equal to the value of the population mean. Okay. So then alternative hypothesis equal to usually the opposite of the null hypothesis. There have three statements. There are three actually. We can actually they classify into three parts: mu not equal to mu naught, mu greater than mu naught, mu less than mu naught. Okay. So if mu not equal to mu naught, so there are actually we can that may be mu greater than mu naught, maybe mu less than mu naught. Okay. But if alternative hypothesis mu greater than mu naught, there are no chances that should be greater than mu naught, and that is the restriction that should be greater than value of mu naught, and mu less, if mu less than mu naught, that should be less than mu naught. So that means these 2 and 3, the alternative hypothesis 2 and 3, this follows the one-tail test, and the first one is follows two-tail test, because they are have two options that may be greater than or less than the value of population mean. So that's why one-tail test and two-tail test is actually, this is actually that concept is coming from the alternative hypothesis that based on the alternative hypothesis. And what is actually for doing any sample, for doing any sampling, so we may have two actually errors. Okay. So there are two errors, type 1 error and type 2 error. So what is type 1 error? Type 1 error is reject H naught, reject the null hypothesis when it is true. And type 2 error means accept H naught when it is wrong. Okay. So if you can consider, if you can see the two errors, so type 1 error and type 2 error. Okay. So which one is the more severe one? Type 2 error is the more severe one, because if your assumption is wrong, but you accept that assumption. Okay. So that's why the type 2 comparison between, actually, if you can compare with the type 1 error and type 2 error, the type 2 error is more severe than the type 1 error. And we can actually have, some level of significance value and the level of rejection, right? This is based on the this actually concept is coming from here. So the probability of type 1 error is we can assume that alpha, and probability of type 2 error is represented by beta. So what is alpha? Alpha is the level of significance. Okay. So here you see the region which amounts to rejection of H naught is termed as critical region. So that means this is the critical region. That critical region is what? Actually, this is the region of rejection, and this is the level of significance. Okay. So Usually we apply the 5% and 1%, the minimum actually what the probability level for significance for rejection region. And this represents that 5%, this is a significance level 0.05, and that indicates a 5% risk of conducting that a difference exists when there is no actual difference. So if the null hypothesis have no difference, okay, we usually assume the null hypothesis, if you have two variables, there have no significant difference between the two variables. So if you can actually this is based, this concept is coming from the p-value. This is actually nothing but a p-value, okay? So this actually, if that is the what the actually that there have no any difference, okay, there have no any difference, but there may have some it may have some difference between this the parameter of any variable, that is the chances of risk factor is only just we assume 5% or 1%, because we assume at as much as minimum, okay? So that's why the 90 confidence interval is high. Okay, so 95% is confidence interval, so that we have the confidence that we assumption is actually the under the true value, under the true in under the corrected region. Okay, so that what this is actually the means I have actually here put one that graphs, means one that graphs where is the critical region occurs, where is the point critical point occurs. Okay, so last let us actually take the steps of this actually testing of hypothesis. So first of all, so first there are actually basically we have 5 steps for doing any parametric test under the testing of hypothesis. First we have to assume the null hypothesis, next we have to assume the alternative hypothesis based on the null hypothesis, then we have to choose the proper level of significance, and then test statistics, then conclusion. Okay, this is the basic steps for doing any test. And that what is p-value? Just see that this is actually the normal probability curve. So here under the normal probability curve, so this is the region. This region is called as critical region. Okay, so this region is called as critical region, and this is also called as critical region. So this is actually that level that is done, that actually divided, this curve is divided into 2 parts. This point is called a critical point, and this significance that level, that critical region is actually this 5% under the critical region and 95% under the most, that means under the corrected region, under the acceptance region. Okay, under the acceptance region, and under the critical, under the rejection region we assume 5%, under the critical acceptance region we assume the 95%. So that means this is our confidence interval, and the 5% is our level of significance. Okay, so here the p-value is what, that this is the probability value. Okay, so this is means level of significance value. So that means how likely you were to have found a particular set of observation if the null hypothesis were true. Okay, so that means what, that it is basically based on the p-value we can tell that your test actually your test statistics, your assumption is significant or not. Okay, so that means based on the p-value means based on the significance, that means what, wow, that your null hypothesis actually that how likely your null hypothesis, how likely, that means what, the you can accept the null hypothesis based on the set of observation. So after that here actually what I'll actually give you the steps how can we means what the do the all the test in SPSS software. So today I'll use SPSS for doing all the parametric test as well as the non-parametric test. And for actually what the t-test, so that t-test is actually first the applications of t-test is the single mean. So single mean means what? That let us take one example. So here, suppose if you have 30 hypertensive males, so that means this is your sample size observation. The observed BMI is 27, the standard deviation is 4. Okay. So also suppose it is known that the mean BMI is no hypertensive male is 25. If so, the question is no, whether or not these 30 observations could have come from a population with a mean of 25. Okay. So that means what is your means what the sample size 30 and what is your null hypothesis? Your null hypothesis will be we have to check the population mean is 25 or not. Okay. So your null hypothesis is population mean equal to 25. So then your alternative hypothesis accordingly, the mean not equal to 25, because of usually why actually we are using mean, we are assuming mean not equal to 25 because we have no idea about the population. We have just only the observation of the sample. So that's why always that we use the two-tailed test. But if you know that if the population, if you know the population mean is always the greater than 25, then you can take. But usually we don't. Okay. So usually mean not equal to 25. So this is actually just examples of one sample. This is what is the actually variable here, BMI, the value of BMI. Okay. So then how can we actually use the SPSS software for this? That means what? The 40 tests per single mean. Now I just what? Stop sharing my screen. Now I want to open my SPSS window. Just wait. Okay. So is it visible now? This is not SPSS window, but this is a one examples of t-test for single mean. Okay. So here, so now this is the examples of what 10 boys have following IQs. These are the some data set. Now we have to test do this data support the assumption of a population mean IQ of 100. That means your null hypothesis is what? The mu equal to 100. Okay. So now we can apply this data set in the SPSS view, and we now then we'll actually find the value of t as well as the p value. Okay, there have some steps. So now again I am sharing my SPSS. Okay. So now this is actually SPSS view. Okay. So here usually in SPSS that we have 4 views, but we deal with only 2 views. Under the variable view, we can apply, we can actually put all the variables, whatever you have. And under data view, we actually we put the data under the data view. Okay. So that under variable, suppose if you have any variable, for example, that IQ, for example, BMI, for example, age. Okay. So now just I am denoting, just I am using some letter. So X, so this is one variable. Okay. So under X, you can put actually, you can put the name of the variable X under the label. Okay. So by default it is coming. So now then what the measures. So this is by default it is coming unknown, but what measures, so what is the actually your measures is the what does us the scale, because under the SPSS we have actually here ratio and interval and ratio, these are under the scale, so that's why you just take it as a scale. So then data view, put the data, okay, whatever you have. Suppose just I am actually what the putting some any numeric data here, just we know how to do the t-test, how to do the different types of test, okay, in SPSS. So here if you have any observations, 10 observations, okay. Okay, fine. So these are suppose my data set. Okay, now I want to see, this is the sample values. Okay, so these sample values is coming from some population. So now we have to assume some null hypothesis that population mean is equal to suppose 50. The population mean is equal to 50. This is your null hypothesis. So now I am going to do the analysis. Click analyze, then compare mean, then one sample t-test, then say they select this variable under the test variable box, and the value of the test value is what? The test value is your means population mean value. So we have already assumed the population mean is 50. So put 50. So just press OK. So then your result is coming here. So this is your result. So your test value is 50 and the t value is minus 0.799. Is it visible to all of you? Okay, I think it is visible. Okay, fine. So degrees of freedom is 9. Yeah, okay, fine. So degrees of freedom is 9. So that means what? 10 minus 1 observation. How many observations I have taken? 10 observations. So it is 10.
It's not visible.
It's not visible. Okay,
Not
fine.
visible. Not visible.
Is it visible?
No, ma'am.
My data set?
Not yet, ma'am. Not yet. Not yet.
Not yet. Okay.
The output generated in next window, no? That's
Yeah,
what it is not.
Yeah, now it is visible?
Yeah, yeah.
Okay, fine.
Visible. Yes, visible.
Yeah, okay. So this is my result. Okay,
Yes,
so
ma'am.
now I have taken 10 of numbers of observations. So that means what the degrees of freedom is n minus 1. So 10 minus 1. Here the degrees of freedom is 9. So the value of t is minus 0.799. Okay, so the value of the significant value is 0.445. So this is actually p value. So here p equal to 0.445. So that how can you interpret with this actually result? So because your test value is 50, if the value of if the level of p value, if p value is equal to, usually what we do the test at 95% confidence interval. 95% confidence interval means what? The 5% level of significance. So 5% level of significance is 0.05 is the value of p. So if p value is greater than 0.05, so then we can accept the null hypothesis. If p value is less than 0.05, then we reject the null hypothesis. Okay, so now our significant value is 0.445, so which is greater than 0.05. So then we accept the hypothesis. Yes, our population mean is 50. Okay, so that means our population mean value is 50. So that means we can accept the hypothesis because of the value of p is greater than 0.445. Okay, so now
This is p value.
yeah, this is p value. So now actually now from this actually data set, from this, suppose now I am applying here some more data. Suppose you want to see that this data set follows a normal distribution or not. Okay. So now okay, so is it visible now? Is my slide is visible? Means not slide, actually SPSS data
Yes,
view.
ma'am.
Okay, fine.
Yes,
So,
ma'am. Yes, ma'am. Visible.
okay.
Visual. Please do continue.
Yeah. Okay. So now then we can take what are the steps for doing the normality test. Click analyze, then descriptive statistics, then what? Explore. Okay. So whatever the variables, now I am applying here for only one variable. So that's why now this is just converted into the dependent list. Okay. So that X only. So I click statistics, not needed statistics. So that plots, under plots, you just click histogram. So then normality plot with test, then continue it, then press OK. So then your result will come under this same variable.
Output not visible, ma'am.
Yeah. Now actually there are lots of views now. That's why now it may visible now.
Yes, yes.
Now it's coming. Yeah. So here the value of this test of normality, you see the Kolmogorov's mean of test. This is 0.221. The value of significant value is what? 0.081, right? Okay. So that in actually Shapiro-Wilk, this is one of the normality, this is one of the tests for checking the normality. That is the value of significant value is 0.190. So here 0.081 and here for 0.190. So these two values are greater than 0.05, is not it? So that means what? If it is greater than 0.05, so we accept the null hypothesis. So that means our data follows the normal distribution. Okay. So now this is the result, and this like as what? This like as bell shape, right? So this means this is actually this follows the normal distribution because of the value of the significance value is greater than 0.05. This is the steps for doing the what means for doing normality test and t-test for single mean. So here now I am sharing my PPT. Okay, so now t-test for related samples. So related samples means what? For pair t-test. Okay, so here for pair t-test, so what we do, we have to take any two variables. So we have to, means the variables is only one, but before and after we have to take the data before and after. If you want to see the effect of any invention, okay, so then we take the data before, after invention, then we take the what? Intervention, sorry. Then we take the data after the intervention. So then what? Then we have two sets of data for single variable before, just there is only one difference, that is the time. Okay, so that means what? On that cases that variables are related, the same variables, that data set and that one means what? The data set from the previous means what? The before the intervention, and data set after intervention. So these have two data set, then we can apply the pair t-test because the each coordinate are interrelated. Okay, so and under the independent sample t-test, what we do, we can apply any actually variable, any variable that may be dependent, sorry, that actually what? That are not dependent, that are independent. if any variables, if both the variables are independent with each other, so then we can apply the independent sample t-test. Okay, but there is a one concept actually for independent sample t-test for actually what that is now I'm discussing with t-test for single mean, t-test for difference of mean, t-test with pair t-test, and independent sample t-test. Okay, so accordingly we have some non-parametric test also for this actually assumption, for this actually condition. For suppose we have two variables, we have to check the efficacy of any drugs before and after, so like that. So then we can apply the t-test. For a parametric we can apply the pair t-test. For non-parametric we can apply the different actually Kolmogorov-Smirnov test. There are different actually non-parametric tests for actually what the same condition. And t-test for two independent samples. So then if both the variables are independent, then we can apply the independent sample t-test. If both the variables are independent but actually that data does not follow the normal distribution, data have no any means what the information, so then we can use the Mann-Whitney test. So there have actually means there have the same means what the application part for different actually parametric and the non-parametric test. But if you have more than two variables, for example, suppose you want to compare between actually what the among 4 variables, 5 variables, so then you cannot actually take that actually what the you cannot means what the check the between two variables. Suppose x1, x2, x3, x4, x5. If you have 5 variables, then all the variables are independent each other, so then you cannot actually test x1 with x2 for t-test, x1 with x3 for t-test. So that on that cases, then you will not get the accurate result. So you have to take the ANOVA, analysis of variance, to compare not among all the 5 variable based on the parameter value. Okay, so based on the why I am saying based on the parameter value, because that is actually we have some common null hypothesis for each and every test. So if in case of independent sample t-test, we can assume the null hypothesis is there is no significant difference between two variables. So then in case of ANOVA, there have no significant difference among all the variables. So then on that actually same way we can assume a null hypothesis for every actually the parametric test. So then t-test is applicable for correlation coefficient also. So that if you are going to see the value of the correlation coefficient, so it is just as a relation between any two variables, but the correlation coefficient, it gives us the relation between any two variables. It's usually actually represented by R, and it is actually what the lies between -1 to 1. And if the value of correlation coefficient is takes the negative value, then it becomes as a negative correlation coefficient. And if it is if R takes the positive value, then it is a positive correlation coefficient. If R equal to 0, so that means there have no linear relation between any two variables. Okay, so but the correlation coefficient, but testing of the correlation coefficient we can use by T. So if the correlation coefficient value of the correlation coefficient is significant or not, and we assume the null hypothesis between the correlation coefficient is equal to 0. Okay, so there have the significant, the correlation coefficient is significantly different from 0. So that's why we usually assume the value of the correlation coefficient, that is Rxy equal to 0 for the null hypothesis. And That correlation coefficient is applicable for the quantitative variable, and if you have the qualitative variable, if you have the ordinal set of data, so then we cannot apply the correlation, means what, the Karl-Pearson correlation coefficient. We have to take the Spearman's rank correlation coefficient to test the relation between the variables. Okay, so now for checking the significant or not significant, we can use the t-test for correlation coefficient. And for the regression coefficient, so maybe you know the regression, that line of regression. This is very actually important methods for means what, the fitting a model, linear model. So what is actually regression? So in correlation coefficient, we usually give the interpretation that variables are related, means okay, they have some relation, they have some linear relation. But in regression coefficient, there have some dependent variable as well as have some independent variables. Okay. So in case of simple linear regression, we deal with only two variables. One is dependent, one is independent. And in multiple linear regression, there have more than two variables, one dependent and others one. All the remaining variables are independent. In case of, suppose the variable, the dependent, if the variable is related to this one or not, this variable, how much influence this variable with this one. So on that cases, we can apply the multiple regression line if you have more than two variables. Okay, so there are different actually regression line. So yes, multiple simple linear regression, multiple linear regression, multiple logistic regression, and the Cox regression. That the regression line is based on the value of the dependent variable, and if the dependent variable is quantitative, then we can apply the multiple linear regression. If the variable of dependent variable, the value of the dependent variable is qualitative, then we can apply the multiple logistic regression. And if the variable, the dependent variable is based on the time, so then we can actually apply the Cox regression. So there are lots of different types of regression based on some criteria, based on some condition. So here, so the simple linear regression, the coefficient, we can test by using t-test. Okay, so that now I will actually show you that how can you do all these methods in SPSS. Okay, though that will be more clear. So then here I'm sharing. Okay, fine. So you just see t-test for difference of mean, t-test for difference of mean. Okay, so here we have two variables, diet A, that is actually diet A, diet B, and if you put diet A, what is the gain in weight, and if you put diet B, so what are the value of the weight of pigs. Here some actually data sets are given here. So here we can assume the null hypothesis that the population mean have no difference. The diet A represents suppose X and diet B represents suppose Y. There have no significant difference between the population mean. Okay, between the population mean, that is in symbolically, if we can use the null hypothesis by using the symbol, so that mu X equal to mu Y. Okay, so now then I can apply here that means what, means SPSS. So suppose these are the data set for one variable. Okay, so means what, for that this is the actually steps for the independent sample t-test. Okay, now I am going to do the independent sample t-test. It is somehow complicated compared with the t-test for single mean. So now this is the value of X. Suppose you have some one more variable I have to put here. So now I am putting here some data set of y. Suppose these are my data set under y, because this is a independent sample t-test, okay? So that's why that should not be equal. Okay, it may be equal, the numbers of observations for x and number of observations for y, it may be equal, but it may not be equal. So that's why here I have put here the value of x and value of y. We have two variables. So now I am going to that I'm here. My null hypothesis is what? There have no significant difference between the population mean of x and y. Okay, so that, but from this actually way I can't do the analysis. First of all, I have to actually take the coding variable. I have to assume the coding variable for x as well as for y. Okay, for x, suppose you want to put 1, maybe some of you may put 0 or 1 and 1 or 2, x as 1 and y as 2. So that's why I am adding one more variable as a coding variable, that is z. Okay, so z here. So now this is again the nominal variable, because only two variables are here. So now the z, because for each x, see here just put 1 1 1. Now just copy this observation and put here. Then okay, so this is the data set. That what I have actually what I did here. So first of all, I actually put 1 for each value of x. Next, again I put 2 for each value of y. So now I can apply for only two variables. One is x for all the values of x and y, and one is z for as a coding variable. Okay, so now I am going to use the steps: analyze, compare mean, then independent sample t-test, because this is an independent sample t-test. What is the test variable? That is x. And what is the grouping variable? That is z, because under z we have the groups 1 and 2. Then again continue and press OK. So that is our result. No, now I am sharing my result screen, output screen. So here my result is this one. Okay, so is it visible to all of you? I think it is visible. So now, so that significant value for here you have actually what? Got the two values of t. Okay, so one is the equal variances assumed and one is equal variances not assumed, because the under independent sample t-test we don't have any information about the variance. So that's why the value of, first we have to check the, if we can use the independent sample t-test, first we have to check the value of significant value of f. Okay, so this is 0.102. Okay, so 0.102 is greater than, what we do in f test, in f test we check the variances are equal or not. You have two variables x and y, so that means the variances of the population variances of X and population variances of Y are equal. This is the null hypothesis. There have no significant difference between the population variance. So if the significant value is 0.102, so this is greater than 0.05, so that means we accept the null hypothesis. If we accept it, so that variances are equal. So if the variances are equal, we have to take the first value of the significant first value of t, so which is 1.125. So here 0.274. So this is the significant value and it is also greater than 0.05. We accept the null hypothesis. So that means our population variances are, population mean are equal. Okay. So this is your interpretation. So this is the steps for doing the independent sample t-test. And now I am going to actually apply for the dependent sample t-test using the some data. Okay, suppose I have only this data set. For the dependent sample t-test now, I have to actually I have to use the same numbers of observation because both the variables are dependent, but the null hypothesis is same for both the variables. There have no significant difference between the population mean of X and Y. So now I am going to apply the steps for the dependent t-test. Okay, so this is the dependent analyze, then compare mean, then the paired sample t-test. So then under this, actually this is called as the paired sample t-test dialog box. And under paired sample dialog box, so just put X for the first variable, then again select Y for the second variable. So press OK. So then your result is coming under the output view. This is my result. So this is my result. So here the value of this is the result of paired sample t-test. That the value of t is 0.854 and the significant value is 0.418 and which is greater. And because actually now I am choosing the data randomly, so that's why the significant value is, because this is nearby the there have not much more difference between the data, so that's why it is coming as significant, or sorry, not significant. So 0.418 is greater than 0.05. So then we accept the hypothesis. So that means that there have no significant difference between the population mean. These are the steps for doing the paired sample t-test. And for now, for the correlation coefficient also. So then how can we do the correlation coefficient? So then in SPSS, suppose this is the data set. Okay, this is the data set, but just I am actually giving you how can we calculate these actually different tests in SPSS. Okay, so that's why I am showing you the steps. So then analyze, then click analyze, then correlate. Okay, so this is bivariate, click bivariate, then both the variables are coming under the the variable box, then again select Y, so click Y. So here the variables, my variables are X and Y, they both are the quantitative variables, so that's why by default this Pearson is coming. But if you want to see if you have the ordinal variable, then you have to click Spearman correlation. Okay, so this is one of the non-parametric test. So now put select OK. So then here is the result. Okay, so Pearson correlation value is minus 0.152. The correlation coefficient is negatively correlated. So that means X and Y are negatively correlated. and the value of significant value is 0.697. Again, it is greater than 0.05. So that means the correlation is significantly different from what? It is significantly different from 0. Okay. So this is actually just the interpretation. This significant value is coming from the t value. So now,
ma'am, please share the output.
Output view. It's not okay. It's not sure. Okay. Now is it coming now?
Yes, ma'am.
Okay, this is our result. So this is the value of the correlation value is minus 1.152 and the significant value is 0.697. So which is greater than the value of the significant value is coming from the t-test. Okay, using t-test. So that means that we have got the value of significance. So no need to do the t-test. Actually, what means no need to do the t-test for checking the significance between the correlation. So automatically this is coming under the correlation value. So that's why this is so simple to get the correlation coefficient value as well as the significance value of the correlation coefficient. So now here, now I am sharing again my data set. So this is the data set. Suppose if you have only two variables based on these variables, same variables, so then we are going to means what the fitting the model of regression x on y and y on x. Okay, so that x on y means what? The value of the x on y means if the value of y, so x is the dependent variable and y is an independent variable, then we'll check the value of the means y. If value of the y is changed, then how much it will be changed, how much x will be changed. So then it will be given by the regression coefficient, and then we check the significance of the regression coefficient using the t value. Okay, using t value means what the regression coefficient actually gives. The regression coefficient is the slopes, and it gives the actually that if y change, how much x will change. So it's just a simple concept. So this is actually given by the b, and if we then given by b, and as well as the regression coefficient is significantly different from 0 or not, it will give by the significance value. Okay, so now just click analyze, then regression, then linear, then put x under dependent box, again put an independent, put y under the independent box, just click OK. Automatically the results will come. So here my results. Okay, so this is the important point, the value of this. Actually this last table, the coefficient table, is important. Here the regression coefficient is minus 0.242, which is negatively correlated, and the value of t is minus 0.406, and the 0.697 is the value of y. So sorry, the significance value for the value of regression coefficient. The regression coefficient is minus 0.242, and the value of significance level is 0.697. So this is greater than 0.05. So that means the value of regression coefficient is significantly different, not significantly different from 0, because we accept the null hypothesis. So now if you have, suppose, more than two variables, we have to use the ANOVA table. So ANOVA means analysis of
Hello,
variance.
ma'am.
Yes.
Ma'am,
Yes,
here
yes.
you took x as a dependent variable and y as independent. But
Yeah.
can we reverse it?
Yeah.
What
we
will
can.
happen if
So
we
then,
reverse it
yeah,
then?
yeah. Okay, so we can reverse actually in place of, suppose this is the line of regression. If x is a dependent variable, y is an independent variable, so then the line of regression will be x on y. Then if you reverse it, so y is a dependent variable, x is an independent variable, then y on x. Okay, so now I am actually just applying some variable. It depends on the researcher. Okay, so that means for the researcher, what is the dependent variable for the researcher? What will be the independent variable for their actually research work? Okay, so now you can reverse into, then your result will be different. If you can reverse the dependent variable and independent variable, then your result will be different. Okay, so now is it clear now? Okay, fine. Let us take, yeah. Okay, so let us take one more example for doing ANOVA table. So then what actually? So then if we have more than 2 variables, for example, we have extra variables, that is Z, okay? Z. Okay, so that is Z. So if you want to compare among these variables, that there have no significant difference among the population mean of X, Y, Z. So then we can use the ANOVA table. Okay. So here some means the observations under Z also. Okay, so now this is my observations for 3 variables X, Y, Z. So, but for actually on this way, I can't actually do the ANOVA. Okay, first I have to put one more variable, that is the coding variable, same as the independent sample t-test. Okay, so under some independent sample t-test, what we have actually done, we used 2 coding variable, one is for X, 2 is for Y. Okay, so now we have 3 variables, one is for X, 2 is for Y, 3 is for Z. So now I have to take one more extra variable, that is coding variable. For example, that is A. Okay, for example, that is A. So that coding variable is here. So sorry. Okay, so now just put the for X, just put 1 1 1 1 1 1. Then again, just copy this observation and paste it here. Then put Y, put 2, 2 2 2. Then again copy the data set for the variable, from the variable Z, copy it and paste it here. So then again 3. Okay, so now do the proper actually steps, use the proper steps, analyze, then compare means, then one way ANOVA, then what, the under the dependent list put the variable X, under the factor put the variable A, because this is a the coding variable here. So here just click post hoc, and to KB usually we use LSD, least square difference, but here 2KB is the better method for checking the significant difference between mean. Why I am using post hoc actually? Because here I am assuming there have no significant difference among the population mean. So that means what? The maybe X and Y have no difference, the population, maybe they have not significant difference, within the value of variable, variable of y and z, they may have significant difference, and x and y may not have significant difference. We don't know, but overall we assume that there have no significant difference among the variables x, y, and z. So that's why post hoc is needed for checking if some variables have significant difference between, if two variables have some significant difference or not. Okay, so that's why I am using the post hoc test, but somehow it is may not be actually what the useful if the value of the significant value is become not significant. So now I am sharing my output view, output result. So this is our ANOVA table. Okay, so between groups, within groups, and total. So this is my significant value of f. In ANOVA we are using f test. Always we use f test for ANOVA, and significant value for f is 0.565, so which is greater than 0.05. So that means if the significant value is greater than 0.05, we accept it. So there means there have no significant difference among the population mean of x, y, z. If the significant value is less than 0.05, then we can interpret, then we can conclude there have some significant difference among the variable x, y, z. But we have to use some post hoc test for checking the significant difference between any two variables. So that's why we have used this, the post hoc test. But for this data set, no need to use the post hoc test. Okay. So this is the steps for significant, actually what ANOVA table for ANOVA, doing ANOVA. And last one is for all parametric tests. How can we do the non-parametric test in SPSS? So now, suppose, for example, suppose you have only one variable now, that is x. Okay. So now just click analyze, and here all the non-parametric tester belongs under the non-parametric test groups. So click legacy dialog. Whatever you want, you can take any actually test from here. Suppose you want to use the chi-square test. So under the test variable list, you just take it under test variable list and press OK. So then your result will come. Okay. So finally, now I am sharing again. This is the steps, because now, this is the first. Actually, this is not a means what? That means what? I have just wait for. Just wait, it is not coming. Why it is not coming? My screen is visible. The data sets are visible or not?
No, ma'am.
No, na? Okay.
Data set is visible, result is not visible.
Data sets are visible, but results are not.
Okay, fine. But in my actually here I am sharing my slide, but it is not visible yet. Okay. Okay, fine. Why it is not coming? Data sets are visible. Okay. So for now, actually, I am giving you some examples for my manual. Okay, fine. Okay. So now what actually we do in different actually non-parametric, the chi-square test. Chi-square test is one of the non-parametric test. Okay. So we usually have some observed value as well as some expected value. So we check the observed value and the expected value are equal or not. But then we have to use the chi-square test for goodness of it. But in health science, it is actually mostly we use the chi-square test for independence of attribute. This is most important test for the health science, because if you have any two attribute that have any association between the attribute or not, then we can use the chi-square test for independence of attribute. Here I am applying two variables. One is smoking habit and one is health condition. So under the smoking habit, we have three categories: non-smoker, NS represents non-smoker, MS represents moderate smoker, and HS represents the heavy smoker. And under health condition, there have two categories: hypertension and no hypertension. So that's why these are the attributes, health conditions and smoking habit. We can take the null hypothesis that there have no significant difference, which means health conditions and smoking habit are independent. Okay, so that means both the attributes have no any they are completely independent. And then we can use the chi-square test for independence of attribute using this data set. And how can we actually put this data set in SPSS? Just actually see here. Suppose, okay, suppose we have that three means what this is that three categories under the smoking habit and two categories under the health condition. So this is 3/2 table. So now I can I can put all the data set under this SPSS view. So okay, fine. So now I am deleting this all the data from here. So because how many variables I have? 3 variables. X represents suppose health condition, Y represents suppose smoking habit, and Z represents suppose the value of the observation. Okay. That's great. So under X, I can put here actually, if you see here, this actually data set here. If you want to put according to the means what, either row wise, you can put either row wise or column wise also. So if you put the data set as as a row wise, so that hypertension, the value of the hypertension is coming first 20, 38, 28 like that. So then we have to actually we have to assume the code for each actually categories. Under the smoking habit, we have 3 categories. So we code as 1 for non-smoker, 2 as moderate smoker, and 3 as heavy smoker. Again, under the health condition, 1 as hypertension, 2 as no hypertension. So that means what? That under this actually this practical, we have to assume, we have to make 2 actually what the 2 means coding variables for smoking habit and for the health condition, and accordingly we have to actually make 1 variables for putting the observations for the variable smoking habit and the health condition. Okay, so first I have to put 1, 2 and 3 for non-smoker, moderate smoker, heavy smoker. Again 1, 2, 3 for non-smoker, moderate smoker and heavy smoker. Again under the health condition, so then 1 and 2 for non-smoker, for hypertension and no hypertension. Okay, so then here I am putting So the value of the means coding value for X and Y and Z. So here 1, 2, 3, again 1, 2, 3, then again 1, 1, 2, 2, 3, 3.
Screen not.
Under, oh yes, it's not visible.
Yes, ma'am. Yes.
Is it visible now?
Yes, ma'am. Yes.
Okay. So my observations are 20, suppose 28, suppose 21, 12, 16, suppose 19. So this is my observations for these two variables for two attributes. So now click means what? The data. First I have to use data, then with cases, then with cases by, this is somehow different, observation under, put under the frequency variable box, then press OK. So then again the results of, so then again click analyze the state, analyze, then descriptive, well, descriptive statistics, then explore cross steps, then cross steps under rows put smoking habit, under Y columns put health condition.
Output not visible, ma'am.
Huh?
Output not visible, ma'am.
Now is it that my steps are visible or not?
No, ma'am. No, no.
No. Okay, fine.
Can you repeat once again?
Yeah. I can. Is it visible now? Is it visible now? Data sets?
The data screen is visible. Yes.
Yeah,
ma'am.
okay,
Yes,
fine.
ma'am.
After putting the after clicking the data with cases by the variable Z, so that Z is the value, Z is the variable where we put the observations for X and Y, and click then analyze. So then descriptive statistics, then cross steps. Okay, so then under the cross steps you put smoking habit under rows, and under columns you put just health condition, then click statistics, and then click chi-square and continue it, and then press OK. So then this result will come. Now I am sharing my result screen. So here, this is my result. Now, so that Pearson chi-square value is here. So the value of the significant value is 0.000. So now we have got the value of significant value is 0.000, which have the meaning. Actually, this is highly significant. Okay. So that what is the null hypothesis here? The observed value and the estimated, sorry, for the null hypothesis is smoking habit and health conditions are independent. Okay. So that means what? That means there have no relation between smoking habit and their health condition. And if it is highly significant, so why it is highly significant? Because the value of significant value of P is 0.000, which is less than 0.05 as well as 0.01. So that means what? If the significant value is less than 0.01 also, it's nearby 0. So then we can say the hypothesis is highly significant. So that means, yes, the smoking habits means what? Smoking habit affect our health condition. Okay, this is our interpretation. So now here I am applying again for, suppose if you have one variable, so then what we apply for non-parametric test? In case of one variable, we can apply K-sample, Kolmogorov's mean of test. So for the one variable, whatever the variable you have, you select the variable under the test variable, you just converted the variable under the test variable box and press OK. So then your result will come. This is the steps for doing the non-parametric test. And for the again for two sample test, suppose this is the two independent sample test. So whatever you want, suppose the test variable list, you put just the value, the variable means x. Suppose under the grouping variable, what I have done in independent sample test, same way you can put the data set for x and y. Then again you put 1 and 2 for the variable x, for 1 and 2 for the variable x and y. So accordingly, in the same way, we can put the under test variable list and put the yeah. Okay, now I am audible. Okay, so then if you for non-parametric test, you just click non-parametric. So then again, legacy dialog. Suppose then if you want to see the k independent sample, if you have more than 2 variables, so then you can select the k independent samples. So then whatever the variable you have, the same way for the parametric test, what we have done for the you have used grouping variable, you have used some test variable, then accordingly you just put under the test variable list and grouping variable box, then press OK. Whatever you want, Kruskal Wallis is here, median test is here, okay, and zone Kira terps tra is this one of the non-parametric tests for independent samples, several independent sample. It is equivalent with the ANOVA table. So does press OK. So then your result will come in automatically. So then again for the two related sample, it is actually it is related with what the what paired t-test. For non-parametric, you can use Wilcoxon, sign, McNamara, marginal homogeneity. So whatever you select, or your result will come. You just select for any variable 1 and variable 2, then your result will come. So these are under the spaces view. Okay, thank you so much. This is my actually course content is over now. So you can ask any questions from your side.
Madam, please explain about the observation values in where I wouldn't get it.
Where observation value means?
In chi-square test.
Okay. So this is my data set. Is it visible to all of you, for all of you?
Yes.
Okay, fine. So now that means what? That suppose you have two attributes where I consider two attributes are smoking habit and the health condition. Yes. Okay. So under the smoking habit, we have three categories. One is non-smoker, moderate smoker, and heavy smoker. Under the that health condition, we have hypertensive and no hypertensive. Suppose. Okay. Yes. So that under the for hypertensive, so we have two categories. So that's why we code as 1 for hypertensive, 2 as no hypertensive, and accordingly. So for X, so then 1 for non-smoker, for smoking habit, 1 as non-smoker, 2 as moderate smoker, and 3 as heavy smoker. Okay, so that what you want actually, how can you put the data set? This is your own actually, what the means this is your own decision to put the data set either row wise. You can put either row wise or the column wise. Okay, now I put the data set here column row wise, so that's why I put all the values, because you just see the value here 20, 38, 28, right? So how many observations you have? 6 observations we have. So 20 is for non-smoker. That's why 1 is coming under the 20, 2 is coming under 38, 28 is coming under heavy smoker. So then again 50, 27, 18, is not it?
Yes.
So that means for 20, 38, 28, again 50, 27, 18. If you have more categories, then again the values is coming. So on that way, we can put the data set in the SPSS view.
Okay. Thank you, madam.
Yeah.
Ma'am, how did you coded these categories into SPSS? I'm not able to understand it.
Yeah, you just put it 1, 2, 3 like that, na? So that means what? The for suppose
Like
yeah.
Like
Yeah.
non-smokers, medium smokers, and higher smoker have 1, 2, 3 code. And
Yeah.
if hypertension is 1 and non-hypertension is 2, then it could also be like that. Na, ki in X column, if we have put it 1, 2, 3, then in Y column 1, 1, 1, and fit 2, 2, 2. Then how
Yeah,
is
you
there
can.
3 also?
No, because 3 means for heavy smoker. Na? You have, because if you have the 2 categories under health condition 1, 2, then under smoking habit 1, 2, then 3 will not come. But if you have 3 categories, na, that's why you have to put the 3 code for heavy smoker.
Okay, I got it. The 3 is for heavy smoker, but in hypertension category, we have only 2 categories, like hypertension and no hypertension. So it should be only 1 and 2. No, how is there 3 also?
No, 3 is not coming here, na? You just see the say means what there means my data set. If you see the data set, just see it. 1, 1, 2, 2, 3, 3. Oh, I'm so sorry to get it, because here 1, 2 is coming. I'm so sorry. Okay, 1, 2, 1, 2. No 3 is coming. It is the way.
Okay.
It is the way.
Okay,
yeah,
okay, ma'am. Now
yeah.
Yes,
Under
ma'am.
X, 1, 2, 3, and under Y 1, 2, 1, 2, 1, 2.
Okay, got it, ma'am. And ma'am, I have one question more.
Yeah.
How did we decide the n equals to 30? Like I have asked before you that population size should be less than 30 for applying the t-test parametric test. So why it is only 30?
Because
if
there
is
have some yeah, so that is actually basically what in every actually what this is the standard actually what the value of the sample size. We don't have any theory. Okay, so suppose why it is 0.05, why it is 95, like that, na? So that means what why it is not 80%. We have
Ma'am,
some
I have read it somewhere ki when it increases from 30s, then it applies the central limit theorem, like CLT.
we can
But and the above 30, the confidence interval increases to give them a normal distribution. But I'm just not sure about the 30, because when we consider the 5% level of confidence, then a 5%, 1% chance we consider just like probability. You have 5% chance of being rejected. But 30, but 30 is like different from 5 and 1. That's why I have question about the 30 number.
Yeah, okay, fine. So that means that I just want to say that what actually the minimum sample size. So because the central limit theorem, it gives actually if your sample size is increases, so then your what the your means that follows the normal distribution and your result will be appropriate. Okay, so if the sample size is greater, means what the larger, then your actually what the repetition, that means if you have the larger sample size, so then you will get the better interpret, then you will get the better result. Okay, so that's why actually our standard value of actually the sample size is 30. So that we have no any theoretical actually what the to represent them that y n equal to 30, but this is the standard actually value of the sample size. If n equal to 30, so then if n less than 30, n greater than 30, it does not represent that we cannot take this. But this is the standard actually theory but that we can apply greater than 30, we can apply this test, we can apply this test, so that there is no any theoretical issue.
Okay, so just the 30 is the cutoff point.
Yeah. Why?
Can you please explain the null hypothesis?
Yeah. So null hypothesis is nullified a statement. Okay. So what we do in the null hypothesis, we assume that whatever your statement is based on your assumption actually. Okay. So it based on the researcher. So it is the null. It means what it have no any difference among these variable. That means they are equal. They are equal. We assume they have no any. We know, suppose they have some significant difference because of this. Actually, we are doing the research, but we assume these are not equal. So we are doing the research. Yes, it is not equal. We have to prove using some statistical test. So this is.
Can you give one example?
Yeah. Okay. Fine. So. Okay, fine. So suppose you know the height is related to its weight. Okay. So height is related to its weight. So that means if you want to see the value of the height is related to its weight or not. Okay. So then we can assume that yes, no, height is not related to its weight. Height and weights are, sorry, yeah. So no, because means what, then we can assume there have no any significant difference. There have no any significant relation between height and weight. But you know that yes, height is related to weight. This will be the assumption, and this is your null hypothesis. Have you got it?
Can you say that linear regression and a logistic regression?
Yeah. So linear regression is what actually? The linear regression is all the values are linearly related. Okay. So that means for the variable of the linear related means linear relation means what? The power of the variable. So power of the variable means y equal to a plus bx. Each variable and its constant, each regression coefficient have only one power. A equal to x to the power 1, b to the power 1. This is have one power. So this is, you know, the linear part means concept of the linear equation. This is just a mathematical equation. Suppose you assume like that. Okay, for in logistic regression, what we do, we apply the dependent, in linear regression, we apply the y as a dependent variable and it is a quantitative variable, and in logistic regression, y is a dependent variable and it follows some categorical variable. This is the difference.
Hello, ma'am.
Okay.
Yeah.
Hello, ma'am. I must appreciate it was a very nicely explained presentation. But can you please suggest a good biostatistic book with plenty of solved examples for step-by-step calculations, like which has solved examples with calculations for academic purposes?
Actually, basically, I am from agricultural statistics. So then, but for biostatistics, now I have to check actually the examples, which means for biostatistics book with example. I can actually, for the basic part, I can suggest you one book. So that actually it is a nicely explained book for actually the basic part of statistics. So that is Rangrashami. So agricultural, but this is a fundamental of agricultural statistics. Okay, so for agricultural book only. So that I'll share my email ID and my contact number. After actually checking, then I can give you the proper answer.
Okay, ma'am. Thank you so much.
Yeah.
Ma'am,
Yes.
what is Cox regression?
Yes.
Ma'am, can you spell the book name
What is
again?
Cox regression?
Cox regression, it is actually time. It is based on the time. If dependent, there have different actually regression. If dependent variable is a quantitative one, then we can use the linear regression, simple linear regression. If the dependent variable is qualitative, the binary, maybe multinomial, so then we can logistic regression. And if the dependent variable is based on the time, so then we can apply the Cox regression.
Okay,
Ma'am, can you spell the book name again, ma'am?
Oh, yes, the Rangrashami book, R. Rangrashami. It's written by R. Rangrashami, Fundamental of Agricultural Statistics.
Okay, thank you. Thank you.
Yes, yes. And S.C. Gupta and V.K. Kapoor, Fundamental of Mathematical Statistics. So there have lots of actually example for general statistics actually, not for biostatistics.
Ma'am, but in SC Gupta, there is a very tough calculation, numerical derivations.
Yeah,
and some
okay. Yeah, somehow it is tough for you actually. Yeah, but Rangasamy, if you can go
Yes.
through Rangasamy, it is a very nice book actually for basic actually concept.
Yes, ma'am.
I think there is no question from the participant side.
Yes.
Most of questions answered by you. And really, thank you so much, ma'am. The presentation was very nice. So once again, thank you to all the participants, and thank you, ma'am. We will meet tomorrow at 6 p.m. Okay, thank you to all.
So the PPT and the video.
Yeah. Ma'am, please send me PPT and I will share the PPT to all the participants. Okay.
Okay, sir. Thank you.
And I
Thank
will
you.
share
Thank
the
you so much.
recordings as well as the PPT
Yes.
simultaneously. Okay. So good night to all of you.
Thank you, sir.
Okay.